Now let's use calculus to compute the area of a circle. So I've drawn a circle of radius r, and I've also drawn an infinitesimal rectangle in the first quadrant of the circle. So that's at x position, x, and it has a height y, let's say. And then the width of the rectangle is dx. So we're going to sum over all of these infinitesimal rectangles in the first quadrant and then multiply the result by 4. So our infinitesimal area here is dA, is the height times the width of the rectangle, so it's y dx. And our y here in the first quadrant is going to be the square root of r squared minus x squared. Okay, so now we're ready to compute the area of the circle. So the area of the circle is given by the sum over all of the infinitesimal areas. And now we are only doing it in the first quadrant, so we're going to multiply by 4. So that's equal to 4 times the integral of dA is y dx. So it's square root of r squared minus x squared dx. And what is the value of x in the first quadrant? It goes from 0 out to the radius, so it goes from 0 to r. So to compute the area of a circle now, we only need to do this integral. This is an integral we've probably done before. We're going to use a trig substitution here. So we want to convert this square root to a trig, a function, so we can let x equals r times sine theta. So it's a direct substitution. And then dx then, using the differential, is equal to r cosine theta d theta. So if we substitute in, we get the area is equal to the integral of the square root of r squared minus x squared, which would be minus r squared sine squared theta, dx, which is r cosine theta d theta, and we're multiplying by 4, so we have a factor of 4 in front. So the area is given by this. Then we can simplify the r squared in both terms. We can factor it and then take the square root, so that gives us an r. And then we have another r here. Then we have the square root of 1 minus sine squared theta, which is the square root of cosine squared theta, which is cosine theta. So that will simplify. Meanwhile, we should probably put in the limits. So let's put in the limits here. So when x goes from 0 to r, theta then, sine theta should be 0 when x equals 0. So theta goes from 0. And when x is equal to r, sine theta should be 1. So theta will go from 0 to pi over 2. So we can put in the limits here, 0 to pi over 2. And then we can simplify. So we have a 4r squared. Then we have an integral from 0 to pi over 2. And then we have a cosine times a cosine, or a cosine squared theta d theta. And then we use our well-known identity for cosine squared theta as 1 plus cosine 2 theta over 2. Now we'll cancel one of the factors of 2. So that becomes 2r squared, the integral from 0 to pi over 2 of 1 plus cosine 2 theta d theta. The integral of cosine 2 theta is minus sine 2 theta divided by 2. And then at the limits, it would be sine pi and sine 0, which are both 0. So the only contribution here comes from the 1. So we have 2r squared times theta evaluated at pi over 2. Or we have 2r squared times pi over 2 from the integral, which is just the 2 cancels. So that's the area of the circle, pi r squared. Okay? So we've shown that by summing up all of these infinitesimal rectangles, we can get an integral we can do. We can use a trig substitution to do the integral, and we can compute the area of the circle is pi r squared. This is not the easiest way to do it. There's an easier way. So let me show you that now by first drawing a graph. So let's compute the area of a circle in a second way. I think this way is a little bit easier. We have our circle of radius r. Inside the circle, we draw 2 circles. They're separated by an infinitesimal distance dr. They have a radius of r. And we can find the area of the whole circle by summing up the areas between these 2 concentric circles. So we're going to have a whole bunch of these little areas and sum them up. So that tells us what our dA should be. So our dA here should be the circumference of this circle times the width, which is dr. So the circumference is 2 pi r, and the width is dr. And then we can integrate over dr to get the area. So the area here is the integral of dA, which is the integral of 2 pi r dr. What is the values of r? It goes from 0 to capital R. So from 0 to capital R. And that becomes, the integral here is the integral of a linear function. So it's 2 pi r squared divided by 2 between 0 and capital R. And then the 2 cancels, and we get pi r squared. Okay? So we get the same formula for the area. Much easier to do it this way. This is essentially using what's called polar coordinates. So here I'm illustrating then to calculate the area of a circle. We can use calculus. We can either do it in Cartesian coordinates by summing up these rectangles, or we can do it in what is essentially polar coordinates by summing up the areas of these concentric circles. We get the formula for the area pi r squared. From this particular case, we see that we're integrating a circumference. So the integral of 2 pi r gives us pi r squared. So the area is related to the integral of the circumference. And using the fundamental theorem of calculus, then the derivative of the area is equal to the circumference. So now you know the connection between the circumference of a circle and the area of a circle through calculus. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.